Hi, everybody. Today we are going to talk about the history of life. So we're going to go through some of the important key steps in the history of life. Certainly not everything, but we're going to get through a lot of the main points. So follow along in your notes, and we will go through this, and we'll cover a lot of the main points. You're going to be doing presentations on this, which you already know. So we'll kind of fast forward through that stuff, but we'll hit a bunch of the other things that happen. So first of all, although there is a lot of life on Earth today, it was not always so. Our planet first formed about 4.6 billion years ago. And Earth at the time was under constant bombardment by things, right? Meteorites. And the Earth was young, and it was hot, and it was molten. And over time, it cooled. And as it cooled, the outermost layer that we call the crust solidified. So that's the layer that we are on, that we dig in, and the oceans exist in. By about 3.9 billion years ago, the Earth had solidified enough to start supporting life. We obviously are never going to know for certain how life started, but we can hypothesize about how it may have occurred. So biogenesis is the beginning of life, and this brings about an important question. All cells arise from the reproduction of pre-existing cells. We learned that when we learned about cells, right? All cells have to come from other living cells. But how did the first living cells come about? Well, one hypothesis is that the chemical and physical processes within the unique conditions resulted in biogenesis. So we had these early oceans that were very hot. There was a lot of radiation hitting the Earth at the time. And so we think that perhaps this mix of the hot oceans, the radiation, some of the gases that may have existed in the atmosphere at the time could have started off the first cells. So the hypothesized series of the stages of the origin of life is speculative, and there's a lot of debate about this model because it's something that we can't really verify very easily. We can collect evidence, but there's always going to be a discussion back and forth about it. And we see here, there's this bubble model that one of the groups may get into as they do presentations. Gases are trapped in underwater bubbles. They react. They're exposed to the atmosphere and to lightning and to radiation. And then from that, compounds can fall into the ocean. So here are the stages of the origins of life. So first of all, we had to have monomers. So organic monomers had to be created. These would be things like monosaccharides, like amino acids, like nucleotides. That had to be synthesized first. And this is going to be covered by a presentation. After monomers, we had to create polymers. So polymers were created, had a lot to do with rocks that could have existed on the surface. So after monomers, we had to create polymers. After polymers, we had to create self-replicating molecules, molecules that could replicate themselves and then split so that life could replicate itself, basically, is what this is getting at. And then after that, the first living cells. So these necessary molecules, their self-replicating ability, have had to be trapped in some kind of membrane. So that was another step. We had to do that to get the first cells, and then over time, cells changed and they became eukaryotic after they were prokaryotic. So monomers, polymers, self-replicating molecules, and then the first living cells. Those are the major steps in the origin of life. So we have an opportunity there for inquiry. I'm asking questions such as, what's the hypothesis at each stage for how it happens? What's the data that supports the hypothesis? Is the data legitimate? Is it valid? And what is the conclusion? All right, and there are some core questions that we're going to be answering. What conditions on primitive Earth provided inorganic precursors for which organic molecules could have been synthesized? How did simple inorganic molecules contribute to the formation of more complex organic molecules like amino acids or nucleotides? How do polymers get the ability to replicate and store and transfer information? And could complex reaction sets have occurred in solution or as reactions on solid reactive surfaces? And these are all things that we're going to be getting into as we study these steps of life. And one more. Why is it likely that RNA preceded DNA? Okay. So more on the history of life. The geological record ties together the history of life on Earth. So as we dig deeper into deeper and deeper layers, we find older and older fossils. So we have this geologic record to help us. Here we see some key events. We have prokaryotes forming. Prokaryotes are the oldest form of life. And then we have oxygen being formed, presumably by those prokaryotes. After oxygen forms, then we can get eukaryotes. And then we can get multicellular eukaryotes. And then we have animals that would be still in the water. And finally, plants and animals can colonize land. That is one of the more recent steps that has happened. Notice how recent animals and plants colonizing land. Prokaryotes was very, very long ago. Other things you need to know about are plate tectonics. You probably know about this, but basically you should know that our crust is divided up into these different sections that are kind of moving around very slowly on the next layer of the Earth, which is the mantle. And because of the movement of plate tectonics, this means that the continents have shifted over time. They used to be joined as one, and they have moved and spread out over time and continue to move. Fossil evidence indicates that the Earth was formed about 4.6 billion years ago, and the environment was far too hostile for life until about 3.9 billion years ago. The earliest evidence that we have for life is about 3.5 billion years ago. So taken together, this evidence provides a plausible range of dates for when the origin of life could have occurred. So this gives us the time frame that we need. So fossils, as we look back at them, as we dig deeper, it shows that life has changed over time. So fossils, of course, are the remains or impressions of organisms that lived in the past. Most are found in what's called sedimentary rock, which is the rock that's formed by grains falling down into the bottom of bodies of water. We can figure out the dates of fossils by using radiometric dating. Now, I'm not sure, some of you may have learned about this in chemistry, but basically, there are radioactive isotopes in everything, and they decay in a predictable pattern. We refer to that as a half-life. Basically, over a certain amount of time, measurable amount of time, we know that half of the radioactive isotopes are going to decay. So we can use the half-life to determine how old a fossil is. Basically, if we have a fossil, we can look at how many radioactive isotopes are left and how many have decayed, and we can use the known half-life of that radioactivity to figure out how old the fossil is. So here's an example of finding fossils in layers of sedimentary rock. There are some questions here for you to look at. What major changes in the environment occurred after layers D and E? So for this one, you should be able to see that in D, it looks like most of these things were aquatic. And now we see a bunch of land animals because they're walking, and land plants. So something may have changed, right? Life may have gone onto the land. It could be that a volcano erupted and laid new sediment and it was above sea level. What inferences can you make about life forms at the time layer A was formed? So we don't really see any fossils in layer A, so it could be that living things were too small, right? They were just prokaryotic and we can't see the fossils, or perhaps there were no living things. If radiometric dating identifies the rock in layer C as 425 million years old, what can you infer about the age of the fossils in layer C and B and D? Well, these fossils are all about 425 million years old. In B, they must be older, and D, they must be younger. Many of the oldest known fossils are called stromatolites, and they are found in layers of rocks that are active in a time when we had a lot of prokaryotes. So these fossils date back to about 3.5 billion years ago. Stromatolites were built up by ancient photosynthetic prokaryotes. So we still find similar structures by similar stromatolites in a few places today. Basically, what these organisms do is they bound films of sediment together to make these next structures, and then they migrate to higher and higher layers. All right, ancient fossils of individual prokaryotic cells have been discovered that are nearly as old as the stromatolites. We refer to these as cyanobacteria. This is a type of bacteria that is still around today, and we think that a form of this bacteria was around before. So this is photosynthetic bacteria. So you have to think, okay, photosynthetic bacteria, what does that mean? Taking the sun's energy and then producing glucose and oxygen from that. So we have a new form of life. So the cyanobacteria is adding oxygen to the atmosphere. And this is going to change the atmosphere because right now the atmosphere is not oxygen. Well, now it is, but at this time, that we're talking about in the history of life, it didn't have a lot of oxygen. So we're changing the atmosphere. You can imagine that's going to cause some things to happen. So by about 2 billion years ago, the presence of oxygen made most environments unsuitable for many anaerobic prokaryotes. All of this oxygen made the environment totally different. The atmosphere is becoming oxidizing rather than reducing, so the chemical reactions are going to change. And the oxygen levels were high enough that anaerobic prokaryotes started declining, and only a few of them survived. The accumulation of oxygen caused a mass extinction event, but it also allowed for aerobic or oxygen-using organisms to evolve. Another thing that happened is that oxygen in the upper layers of the atmosphere, the oxygen is going to react with other oxygen, and it is going to form O3, also known as ozone. The ozone that forms in the upper layers of the atmosphere is going to cause an ozone layer or an ozone shield, which is going to block a lot of ultraviolet radiation. This is going to mean, because we have the blocking of ultraviolet radiation, that animals and plants that could only exist in the water may be able to move to land, right? The water kind of acted as an ultraviolet shield, but now we don't necessarily need that now that we have the very important ozone layer. The ozone layer could not have formed without the presence of oxygen. All right, so the oxygen revolution posed a challenge for life. It provided an environmental pressure for the evolution of aerobic metabolism. And because of the ozone layer, it allowed organisms to exploit new ecosystems that were not available to them, ecosystems on land. The evolution of aerobic metabolism was significant because aerobic organisms can harvest more energy when they use oxygen, right? We know that using oxygen makes organisms way, way, way more efficient than not using oxygen. So now that we have oxygen, and now that we can use it to make more energy, organisms can become bigger and they can become more complex. And perhaps they can even become multicellular. So this is going to be a big change. Having oxygen in the atmosphere is going to change life completely. And so from there, we go back to, this is the end of the PowerPoint, but if we go back to here, we see that now that there's oxygen, we can have eukaryotic organisms. Notice how they're starting to get more complex. We can have multicellular eukaryotes, even more complex. We can have animals, so organisms that eat other things. And then plants can colonize the land, and then animals can colonize the land after plants do. So there's a lot going on there. We are going to end here. Let me know if you have any questions.